So I hope you guys enjoyed Spartan Day. In order to make up a little bit of time for missing lecture today, I just wanted to give you this quick overview video and talk about the parts of the chapter that we've already covered, briefly review those, and then get into electron configuration. So you remember we started this all off by talking about light, and we talked about wavelength, we talked about frequency. I talked a little bit about amplitude, but we really focused on wavelength and frequency. And then we looked at the electromagnetic spectrum. We looked at the trends. So if you look at these trends up here, right, increasing energy to the left, increasing frequency to the left, and increasing wavelength to the right. That took us to the speed of light equation. So the speed of light is equal to wavelength times frequency. Remember these two symbols, one of them is lambda, that's wavelength, and the other one is nu, that is frequency. We then talked about the photoelectric effect, and the photoelectric effect essentially says that there is this photon, basically, right? And that that everything that Max Planck derived is related to this E equals h nu. So that led us into this wave-particle duality, where we have to treat the photon now as both a wave and a particle. Again, we got to this energy of the photon, and the energy of the photon was equal to h nu, but it's also then equal to hc over lambda. So we also started to look at the emission spectra and recognize that this pattern for the emission spectra, and this is now the Bohr model, which is the model for the hydrogen atom, and that now corresponded to these different wavelengths of light, right? Individual wavelengths, that was crucial. So here's the model a little expanded. You've got the absorption on this side from the ground state. You've got the absorption from the first excited state, and then you've got the emission spectra on this side. Again, relating back to the idea that it is by integer, right? And so these energy levels are by integer, they're defined. You can tell that they're getting closer as you go up in energy, and all of that was related back to the hydrogen atom and the electrons in the hydrogen atom. So this was that summary of the photoelectric effect that we talked about. So we're looking at which of these is false and which of these is true, these statements. So increasing the brightness increases the kinetic energy. It really is false because increasing the brightness only increases amplitude. It doesn't actually increase the energy of the photons coming in. It just increases the number of photons. And so that's really not going to increase the energy of the kinetic energy of the electrons. The second one, increasing wavelength of incoming light, increases the kinetic energy of the ejected electrons. That's not true because increasing wavelength actually decreases frequency, and you need to actually increase frequency to increase the kinetic energy. So increasing the brightness of incoming light increases the number of ejected electrons. That one is true because now you've got a larger packet. So think of it as when you increase the amplitude, you're actually increasing the number of photons hitting. And then the last one, increasing the frequency, increases the number of ejected electrons. It's true because it's going above the threshold energy, but not really true because increasing the frequency is not going to increase the number of ejected electrons. So that one's a little bit of a true and false. So now we move on to Bohr to quantum mechanics. And it starts with the idea that the the wavelength. So now we're looking at the de Broglie wavelength. So the de Broglie wavelength is equal to h over, remember, mass times velocity, right? And the idea is that, and this goes to the particle-like character, right? That these electrons are moving in waves around a nucleus. And so it only really is effective to look at the wavelength of really small particles. Remember, this mass term and this velocity term have to be relatively large to get a wavelength that's reasonable, because this is still 6.626 times 10 to the negative 34. So here's the de Broglie wavelength equation. And also, we have to look at physics. And if we look at the physics of a particle, right, the classic trajectory is on this side. But if you look at the quantum mechanical explanation of the movement of electrons, it's this probability distribution over here, right? And so that's what we mean when we don't know exactly where the electron is. But again, back to the idea of energy levels. So this is an energy level diagram for the hydrogen atom. And if you look at the energy difference between one level and another, you can get that delta E, and delta E equals h nu, or hc over lambda. And if you, again, solve for lambda, you can get the wavelength of either excitation or emission, right? So this was the worksheet that the last question I told you to go ahead and check your work on here. So remember, we identified all the quantum numbers, n, l, m sub l, and m sub s, right? Each of those had allowed values. N can equal 1, 2, 3, as high as you want to go. L can only go 0, 1, 2, up to n minus 1. And then m sub l is equal to negative l through 0 to plus l. And then m sub s is the only one that has just 2 all the time, 2 values, plus or minus 1/2. So the m sub l values are defined by L, and L, right, these are defined as s, p, d, and f orbitals, 0, 1, 2, and 3. And so these are the different orientations of the orbital, right? So the s orbital has only one orientation, the p 3, the d 5, and the f 7. So a total of, if you are asked in the fourth energy level, how many total number of orbitals are allowed? This is the allowed values, right? Remember that. So in the fourth energy level, there are 16 total numbers of orbitals. How do you get that? Well, you add 1 and 3, that's 4, plus 5 is 9, plus 7 is 16, right? But you can generalize that and say, for any n value, right, it is the square of the n will give you the total number of orbitals. So this is just to emphasize when the electron absorbs energy, right, that's an excitation. When the electron relaxes and releases energy, right, that's emission. So defining the shapes of orbitals, this is, if you remember, I said that h psi equals E psi is Schrodinger's equation, and every solution was an orbital. Well, this is actually psi squared. Okay, so this gives you what we call the probability density. Okay. This one gives you it in a distance probability. So this is the distance from basically from the nucleus. This one's just a better representation of that. It's called the radial distribution function. And the reason it's a little different is because the electron cannot be at 0, right? That's the nucleus. And so that factors that in, and it gives you that nice curve. And this then gives you the distance that the 1s orbital occupies from the nucleus. This just shows the 1s, 2s, and 3s. Interestingly, right, each of these, the 2s and the 3s have what we call nodes, areas where there's 0 probability. That 0 probability means it can't be there. This is one of the interesting parts of quantum mechanical theory is that, it can be here and here, but it can't be here. So how do we deal with that? We have something called tunneling, and we use that to explain that. But it just shows you the size, the overall size of these. And going from 1s to 2s to 3s, obviously these are increasing in size. This is the P, right? So here is the PX, here's the PY, here's the PZ, right? And they have that dumbbell shape to them. And here's the radial distribution function. You can see they're a lot further, and this is the 2P, right? So it maxes out further out than a 2s or a 1s. Here are the shapes for the Ds, right? Getting more complex. Here's my favorite, the one with the donut, right? The dz squared. And these are just showing the different shapes allowed. So each now of these first 4 shapes have 4 lobes, and then you've got the dz squared that has the 2 lobes and the donut. And finally, looking at the S up top here, the P, the D's, and then finally these guys are all the F's, right? And so the complexity increases as you go from S to P to D to F. Okay, so now this is preview time, right? So we're going to start talking about electron configurations on Thursday, and so I want you to just get a flavor for how we're going to do this. So again, L values of 0, 1, 2, 3, well, that designation is S, P, D, and F. So energy values now, right? The 1s is at the lowest energy, then the 2s, right? And then the 2p, and then the 3s, and then the 3p, and then the 4s, and then the 3d comes in, right? And now you go back to the 4p. And so going up, right, the electrons are going to fill in this order. 4p up to 5s, 5s to 4d, 4d to 5p, 5p to 6s. Now we come all the way out to the 4f. And then we go to the 5d, the 6p, the 7s. And then again we go all the way out to the 5f, and we end up filling the 6d, and we're done. So what are our designations? Well, we talk about electrons by saying the n value, so in this case 1, and then the L value, S, right? And that S then tells us how many different orientations there are and how many different how many electrons are going to be allowed in that. So this is 1s1, right? The next would be 1s2, that would be helium. And then you would go to the second energy level because you'd be at the end of the periodic table. And then you'd start 2s2, and then you go 2p6, and we'd go on. So this would be used to show electrons going into these different orbitals, right? And so these boxes are going to signify the orbital orientations. So that would be 1s1, 1s2, 2s1, 2s2, 2p1, 2, 3, 4, 5, 6. Notice when I do that, right, I put one electron in each open orbital before I pair them up. Okay, so now 3s1, 3s2, and again we're going up by energy, and then you go 3s or 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, and when my arrow is pointing up, that means the m sub s is plus 1/2. When my arrow is pointing down, it's m sub s equals minus 1/2. Okay, and that's just by convention, right? It wouldn't matter. It just matters when you pair them. The other one has to be the opposite sign. So here are the first two, well, the first row and half of the second row, right? So here's the 1s1 and then the 1s2, and then here's lithium in the second energy level. So here's 1s2, 2s1. Here's beryllium 1s2, 2s2, boron 1s2, 2s2, 2p1, and finally carbon 1s2, 2s2, 2p2. And so carbon has 6 electrons, right? Boron has 5, beryllium has 4, lithium has 3, helium has 2, and hydrogen has 1. And so each of these designations tells us exactly how many electrons. So here's a continuation of the second row all the way out to neon, where everything's full. All right, that is the octet. The second energy level has 8 electrons. Those 8 electrons mean that it's at the octet, means that everything that is available is full. So I like this just because it shows you the way in which these fill. Okay, so imagine a wall here, all right? And you start by filling the 1s. You come down through there, you hit the wall, you got to turn back around and go back. You come to the next one, right? That's 2s. Hit the wall, go back. The next one is 2p, then to 3s, right? And then to the wall, back out, and then 3p is available, right? So you just keep doing that, and this gives you a good way to recognize the fill order. All right, so last thing to look at before we talk about this on Thursday, and that is when we talk about the electron configuration, it turns out that the only ones that we really have to worry about are the highest n value electrons. N being the principal quantum number, the energy level, however we describe it, right? So the third energy level, so sodium, for instance, has 1s2, 2s2, 2p6, 3s1. The third energy level is the highest n. It only then has 1 valence electron, right? That is what determines everything about bonding. Now, when you get to be experts in this, which you probably aren't going to be allowed to do in this course, but eventually you could get to the point where you could say, okay, I know that there's a core configuration, and that core configuration is neon, and sodium is in the third energy level. It has 1 electron in the 3s. All right? So we'll stop there, and I'll pick this up on Thursday.